Hey everyone, I just wanted to jump in here real quick with two things before this episode starts. Number one, sometimes in this episode I'm going to sound a little weird, and that's because I'm moving this week, which is exciting, but it meant that some of my audio got messed up when we were recording. Kyle, our amazing producer, has been able to fix a lot of it, but there are times when I sound like I am a fleshy mech being driven by an AI robot. And I swear I am fine. You will never be able to tell the difference most of the time. But, if you're wondering, that's what's going on. Just wanted to be upfront. The second thing I wanted to tell you is you're great. Thanks for listening. We really appreciate it. We could not do this podcast without your questions, but we also just love to hear from y'all. So thank you for your phone calls and your voicemails and your emails and your social medias and all of the things. You make this show better just by being you. So thanks, and enjoy the show. Hello and welcome to That's Absurd, Please Elaborate. I am one of the hosts of this show who talks. I'm Trace Dominguez.
And I talk also as host Julian-focused.
This is a show where the two of us science communicators answer your ridiculous, absurd, wild, out there, far out questions, and we do the science behind those things, or to try at least to get into the ballpark of the answers of some of these questions. Honestly, sometimes I don't know why you send us the question, but we're into it.
We're doing our best. Stop yelling at us. Please be nice to me.
That's right. We're
trying really hard.
Yeah, that's right. We make this show every week, and we answer questions from you, our listeners. So please go into the show notes if you have a weird or absurd question that you want to send us. There are so many different ways to get it to us. But each week we answer 2 questions, unless we have a guest, and then we answer 3 questions. But anyway, this week we have 2 questions from 2 different listeners. Julian, you can go first here. What is your question that you're answering this week?
Yes. First up this week, question sent in by Becca, but actually it's from Henry. And Becca is Henry's mom.
Henry was afraid to send in his thing, so I used an AI thing and typed up her email. You want to hear it?
Okay. What voice did you make the AI speak in? I guess I'll find out. Go ahead.
Hello. This is an AI voice reading a note from listener Becca. This question comes from Henry from Michigan. Henry is 9 years old and loves your podcast. He is so excited that you want to answer his question, which is, are humans the only animal that sleepwalks? He's not really sure why he was thinking about sleepwalking, but he loves listening to educational podcasts and especially loved the episode about fart rockets. Henry wants me to quote, Ricky, I specifically told you not to switch to an all-cabbage diet. Thank you for your awesome podcast and for answering Henry's question.
Ricky comes up a lot post that episode.
That's why I had to make it into the AI voice. It just couldn't be.
Well, now we're going to I think we've opened ourselves up to legal action from Scarlett Johansson, because that was definitely very similar. No, totally different. It's OpenAI's voice, which of course is not modeled in any way on Scarlett Johansson.
No, we did not pay for OpenAI for that.
Okay, good. We stole some AI. It's only fair.
Yeah. They steal, we steal. That's how it works.
Okay. Yeah, that's what we're teaching the kids, Henry. Don't steal, and also
don't pay for AI, I think.
Stuff for yourself.
Don't pay people who stole other people's stuff.
Yeah, you're implicated in the crime. Okay. So, dubious ethics of AI aside, let's keep going. So, right, Henry asks about, do other animals sleepwalk? And honestly, sometimes we're picking questions, and some of them really speak to me, and I know they're going to be a lot of work, and some of them speak to me, and I also know, it's going to be easier to do this one. Maybe I'm tired, I just did a bunch of math for the last one. I want, something that I feel like I'm going to be able to find an answer a bit faster. And this is one of those questions where I read it, and I'm like, oh, man, I bet this is a slam dunk. And you know what? It wasn't.
Uh-oh.
It really wasn't.
What?
But
that's surprising to me.
Yeah, me too.
Well, I mean,
But
I
we'll get
guess
to
that
that.
was that whole lead up was you saying that is surprising.
Can you imagine I explained all that and then I was like, and it was super easy. Here's the answer.
And you know what? I was right.
I'm really smart. Okay.
Okay, yeah, I see your point. Point taken.
Right. Okay, so let's talk about sleep a little bit because I think it's important to also define like what sleepwalking is. But I do think it's interesting because as I did this research, I did discover I think there's a misunderstanding about what sleepwalking is.
Okay.
And what people think sleepwalking is not technically sleepwalking. So now that I've primed you for failure, Trace, what do you think sleepwalking is?
You know, I used to sleepwalk.
You did?
I mean, when I was like a little kid, I guess. I guess it's more common in children. And
Yeah.
my parents said that I would sleepwalk, and I was in the bedroom upstairs, and my parents, I would come downstairs and like talk to them while sleeping,
Oh.
apparently. And then they would
Weird.
tell me to go back to bed, and I would be like, okay. And then I would go back upstairs and go back to bed. So what they started to do is just shut the door to my room, and and they could just sit in the living room downstairs and hear me
Just crash into the wall.
hitting the door, not being able to get out of my room. So that's how they solved the problem.
Wow, yeah, that's easy.
Yeah.
If your children are bothering you, lock them up.
Just shut the door.
That's-
Just shut the door, you guys.
Oh no, I'm sorry, Henry, if this comes back later. Okay.
No. Anyway, so what is sleepwalking? I mean, my guess is I'm asleep. My brain doesn't tell my body not to do stuff, and then I walk around, I guess.
Yeah,
I like act
Yeah.
out.
I
eat
think
stuff,
what
or
most-
like walk around and, I don't know, eat. I don't know.
that could be part of
Talk
it.
to people, I guess.
Hang out, catch up on the news.
Yeah.
Get some exercise in while you're asleep because it's so hard these days.
It's
you know?
really hard. You know,
I'm so busy.
so many hours in the day. You know, you
yeah,
really just
if
need.
I could do sleep hiking,
Oh,
I
that'd be
think that
great.
would be
Yeah.
that would be great.
It'd
be a lot
feel
healthier.
good. I'd wake up feeling really good.
But specifically, what a lot of people think when they hear sleepwalking is they're like, "Oh, you're acting out your dreams."
Yeah.
That is
Bigleyizing.
right. Except that's not what sleepwalking is.
Oh, what is?
Yeah.
Wait.
That's a different disorder
Ooh.
that has some moving around in your sleep associated with it.
Yeah.
But it is not technically the same thing as somnambulism.
Somnambulism.
I know. Anytime you can get a good, it's such a nice portmanteau, right?
It is nice.
Somnia,
Yeah.
ambulism,
Yeah.
somnambulism.
Sleep plus walking. Makes sense.
That's exactly what it is.
Yeah.
Okay. So to clarify why it's different, let's talk about the different stages of sleep, right?
Got it.
When you are asleep, there's two major components to it, right? Two major different phases. There's REM sleep, rapid eye movement, REM,
Mhm.
and then very imaginatively, when you're not in rapid eye movement, it's non-REM sleep. So
Cool.
yeah. So non-REM sleep, you can break down into three stages as well. So in the first stage, your brain is firing in a characteristic pattern that is called alpha waves,
Yeah.
right? So your neurons have a voltage change. The frequency of this voltage change is 8 to 12 hertz, which means 8 to 12 times a second, you have these brain waves, these voltage changes. And this is kind of the phase where you're still sort of awake, but you're more relaxed. It's that transition phase. And this
Yeah.
lasts for about 1 to 7 minutes typically. And then this pattern of your brain waves slowing down, but the amplitude of the waves, so the voltage changes getting bigger, continues. In stage 2, these waves are theta waves. They have a frequency of 4 to 8 hertz. Stage 2 lasts about 10 to 25 minutes. And then the third and final stage of non-REM sleep is when your brain waves are really slow. That's between 0.5 to 4 hertz. So that means you might have a brain wave 1 every 2 seconds when it's really, really slow.
Yeah.
So they're the lowest frequency, they're the highest amplitude, and this stage lasts about 20 to 40 minutes.
Wow.
And then after that, you go into REM sleep. And we'll get into REM sleep in a second. But sleepwalking actually takes place during stage 3 in this very deep part of sleep.
Huh.
So it's
Okay.
not during REM. REM is when you have the most vivid dreams. You can dream during every phase, but REM, they're the most vivid.
That's what
so
we associate with dreaming. Even though you can dream
Yes.
other times when you're like, oh, I had this really crazy dream, you're probably in REM sleep.
Yes,
Got it.
exactly. So during stage 3, what scientists think is happening is there's some kind of miscommunication between the parts of your brain that regulate wakefulness and the parts of your brain that tell you to, kind of chill out, slow down a little bit, right?
Mhm.
So the parts of your brain that are associated with wakefulness is the reticulated actuating system.
What? No, that's not it.
I know.
That sounds
Listen.
like one of those things that you see in a Mech Warrior video game.
Every brain term is needlessly over the top. Like they go so hard.
Neuroscientists are very extra. We all know this.
There's so much, and it sounds so complicated because it is.
It is. It's the brain.
But it's like so impossible to keep track of everything. Every time I have to do anything related to the brain, I know I'm just going to be in like a medical dictionary. Like, what are they talking about? Okay, so that's the kind of system of your brain that's associated with wakefulness, and it releases hormones that stimulate you being awake and active in all the parts of your brain, functioning at a higher rate than they do in deep sleep.
Got it.
Whereas for the sleep cycle, that's regulated by the ventrolateral preoptic nucleus.
Oh, no.
I hope you're taking notes. There
I've
will
got
be a
the
test.
ventrolateral VL. What's the other words?
Preoptic
Nucleus. Wow.
You
With an O.
got it. Great.
So blop, blop.
Yeah,
nah,
ventrolateral preoptic nucleus. Okay.
Bullpon.
So
Done. Got it.
sleepwalkers have an issue where it seems like the reticulated actuating system
Yes.
hasn't taken the hint that it's on break. Like, you could chill out now, buddy. You're done for the day. Like, the ventrolateral preoptic nucleus has it from here.
The Vlipon has it. RAC. RAC. No.
Pal.
Pal.
Let's call it pal.
Pal. Pal.
Okay. And the issue seems to be that some parts of your brain are still stimulated like they would be in wakefulness. The brain waves that we look at in these parts of the brain are more similar to like how they are when the person's awake. These parts of the brain are, unsurprisingly, the motor cortex. So that's the part of the brain associated with coordinating your movement. And then the limbic system is also affected. The limbic system is involved in behavioral and emotional responses, especially those related to survival, like getting food, right? Reproductive good times.
Yep.
And your fight or flight responses.
Oh, okay. That's important.
Now, there is one part of the limbic system, though, that is not active, and that is the hippocampus.
Good old hippo.
Which is not a college for pachyderms. Wait, what are hippos? I don't
The
know what group they belong to.
hippocampus.
But anyway, but the hippocampus is related to forming memory. It takes episodic memory and it helps you process it and store it in long-term memory, which I think is really funny. We got a recent question from a listener who was asking about memory, and they were like, I also want to thank you guys because this podcast helps us sleep. So
yeah.
I don't know if I should be offended by that.
No,
I'm
no,
not.
It is weird.
I
but,
put this show on when I'm falling asleep too, but that's just because I'm a horrible narcissist.
Do you really?
I just listened to it back and I'm like, man, we're funny.
Sometimes
we're so
I
funny.
do listen to it. I'm like, that's funny. That's funny.
Oh, tell me the things I learned a month ago, me, but I've since forgotten in the time it took us to edit and upload. Sometimes I listen back and I'm like, wow, that's really interesting. And then I'm like, wait, I'm the one who did the research on this. So my hippocampus, not great at storing a lot of these things I'm learning long term. Okay, but that's part of why, right, like people have no memory of sleepwalking. That's not actually generating any memories while they're sleepwalking around.
Mm-hmm.
Again, though, that's distinct from what Mike Birbiglia, one of my favorite comedians, the disorder he has, which is REM sleep behavior disorder, or RBD.
Mm-hmm.
And that, as the name might suggest, takes place during
REM.
Yeah, it's right there in the name.
In the name, they kept it easy for you.
Now, the REM sleep behavior disorder, that is also an issue with what's the system that controls, falling asleep? I told you that would be coming up in a quiz.
VLPON? Ventrolateral something?
Preoptic nucleus.
Hey, that was pretty close.
Yeah, and look,
See, mnemonics are a big deal. They're really helpful because then I was just like, what's the silly mnemonic I just came up with? VLPON.
There you go.
Ventrolateral preoptic nucleus. Done. Now I'm going to remember it forever. Dang it. Taking up valuable brain space with this.
In your hippocampus.
On my hippocampus. Which now I'm just picturing
build another building on the hippocampus.
Cartoon hippos with carrying a bunch of books around a very sunny campus, I feel like. Because, they make their own sunscreen and it's red.
Wow.
And in their skin.
Now I've learned that, and I will forget it until a month from now when I listen back to this episode. Okay. But yeah, during REM sleep, this system is supposed to release neurotransmitters that block the motor kind of instructions from your brain from actually getting to your muscles.
Got it.
So they release neurotransmitters. A big one is GABA, G-A-B-A. Mm-hmm. I'm not going to say the full thing.
Yeah, it's a big one.
It's an amino acid. And that blocks these signals. It's basically like you're dreaming and you're putting in like controller inputs. It's like you're watching a video game and you've got an unplugged controller in your hand and you're like pressing the buttons.
Yeah.
And things are happening on screen.
Yeah.
But your button inputs aren't doing
anything.
Doesn't matter. I've heard of parents who do this with kids, like who want to play. You want to play Dark Souls with them, and you're like, "Here, buddy."
Yeah,
just hand them like
a controller for a completely different game system.
Becca, I'm so sorry if I'm ruining some parenting tricks
for Henry.
For you,
Henry, always check to see if it's plugged in, buddy.
Yeah. But for people with RBD, it seems like these neurotransmitters, either they aren't releasing them enough or they aren't working or something is still allowing the signals from their brain to actually go to their muscles. And so they are, in effect, acting out their dreams. And that can involve getting up and moving around. So things that look like somnambulism, but they're part of a different disorder. And it can be dangerous. Yeah. Like Mike Birbiglia jumped out of a motel second-story window.
He makes it sound hilarious, but in reality, that is terrifying.
Yeah. Or a good friend of ours, Jared, who since is no longer with us, but he had an issue with, I think it was RBD. And like Birbiglia, like had to sleep zippered up in a sleeping bag, like buttoned up tight. So he wasn't a danger to himself or others. There was actually a guy, Kenneth Park, in the 70s, who was acquitted of murder because he claims he was sleepwalking when he stabbed, I think, his mother-in-law and his father-in-law, his father-in-law didn't die, but his mother-in-law.
Oh, wow.
Yeah, his defense was like,
I was asleep.
I wasn't awake for it.
Sorry, I was asleep.
Right?
Yikes.
During somnambulism, at least, the prefrontal cortex, which is the frontal part of your brain that's involved in decision-making, that is asleep. So I don't know if he was sleepwalking or had ABD, but either way, he said, like, listen, I'm not making the decisions here. I'm not in control.
Yeah, somebody else is at the wheel here.
Yeah.
In this case, not Jesus.
Unless he's dreaming he's Jesus.
I don't actually know how that works.
Loaves of bread. I don't know.
Yeah, slicing bread. It's a bread slicing inventor. That's what he's doing. Ooh.
Oh, that's a shame. Okay, with this baseline kind of made, this bed prepared for us to lie in.
Yeah.
Now let's talk about if animals experience sleepwalking or even ABD, right?
Yeah.
I would be willing to stretch kind of just any sort of moving around in your sleep.
Kind of disorder thing. Yeah.
Yes.
Yeah.
And I really couldn't find anything on it.
Nothing.
I emailed, first thought I had, I'm sure you did too, was we know a scientist who specializes in sleep disorders.
That's right. Vanessa Hill, she's been on the show.
She's been on the show. She's delightful.
She is.
She responded to my question immediately. I said, hey, I'm doing this question. Please, it's for a young boy. I need it.
For Henry.
I need to tell Henry the answer. And she was like, I don't know. She said there's research on other sleep disorders. She pointed me to a lovely French scientist who takes care of narcoleptic dogs that he studies.
Oh.
I know. And like these dogs, he knows certain foods that get the dog really excited will trigger the narcolepsy.
Oh, no.
I know.
That's amazing.
But when it came to like somnambulism,
yeah,
there's a dearth of anything. I tried Google Scholar. I looked around. Vanessa Hill's response was like, I don't see why it wouldn't be possible, but as for actual research on it, I don't know. And so I looked into it. I found a study from 2003 that basically said there's no evidence of it in primates. Maybe that's because we haven't studied it enough specifically, or maybe there's some important fundamental difference between us and other primates that took place when we branched off, on the evolutionary tree. And for some reason, like, our brains are capable of this disorder, but others aren't. It even said that apparently Jane Goodall doesn't think chimps can sleepwalk. Which is very specific.
That is very specific.
I couldn't find Jane Goodall herself saying it, but according to this 2003 paper, that's the take.
Know a lot about the primates.
Yeah, I found a study from the 1960s.
Okay.
I had to go back that far from Dr. Michel Joulet.
Okay.
I probably just made that up.
Michel Joulet.
Who studied cats.
Do cats sleepwalk? I mean, they know they twitch.
Okay, but they don't fully sleepwalk unless apparently they have brain lesions in certain brain structures.
Oh.
And then these brain damaged cats can sleepwalk. Oh. And they're also totally fine awake. Like it doesn't seem to inhibit their behaviors otherwise. But then when they sleep, this part of the brain that was damaged doesn't work.
What?
And I guess it results in sleepwalking in these cats.
Oh my gosh.
But no, that's like it. In terms of sleepwalking as a disorder, that's it. But here's the cool thing.
I mean, before you go to the cool thing, I want to say that is already kind of cool. Like there's a thing that we do that we either haven't seen or don't know if any other animal does. Like that's actually pretty awesome.
Right. And it has interesting possible insight there for, evolutionary biology. Mm-hmm. So Henry, if you're considering going into STEM fields and you still are interested in this sleepwalking question years later, something to think about.
There's true.
Not a lot of research there that I could find. But, okay, here's what I think is interesting.
Okay.
We think of sleepwalking and RBD as disorders, sleep disorders, right? And I can see a case that you could make where it would be a disadvantage to basically, if you're like sound asleep in your nice cave as your cave human ancestor was, if you just get up and wander out of this cave.
Probably bad.
Or wander out of the safety of the small, like, communal dwelling that you share.
Yeah.
To where, like, predators
You're
are.
in the trees and you wander like Wile E. Coyote off of a branch.
And you have no perception of, like, the world around you.
Yeah.
How that could be a disadvantage.
Yeah, that evolution would be like, let's shut this down.
No
You're not going to breed.
But what about sleepwalking as an adaptation? Like, what if there was a way that it could be beneficial?
Tell me.
Okay. So I looked into it. And I did find, when I was really plumbing the depths of, like, where can I find stuff on animals and sleepwalking? I came across a Reddit post. And normally I don't cite them as, like, you know, a trustworthy source.
No,
but I think it pointed me in an interesting direction because they talked about how pet cockatiels.
Wait, what?
Often, yes.
That's a
pet
bird.
Cockatiels, yes. They often have night frights.
Really? Oh, no.
Yes. Where something will kind of jar them in the middle of the night, and they'll, without even waking up fully, they'll start flying, and then they'll hit the inside of their cage, and then they'll be all panicked, and they can really hurt themselves. And it pointed me in this direction of research on birds and how birds sleep. And it turns out many birds sleep differently than us. They do go through the same stages of, like, non-REM and REM, but they're much shorter. Non-REM sleep is like 2.5 minutes for some birds, and then REM sleep is all of 9 seconds.
Oh, wow. Okay.
It's a very brief dream.
Yeah.
If it were like a sleepwalking disorder, right, that, like, you walk around during REM sleep, all of 9 seconds, I can see why that might even be difficult to study, if it even exists there. But a lot of them are also capable of unilateral slow wave sleep.
Oh, like the half of the brain situation.
Yes, half of their brain goes through these sleep cycles and half of their brain doesn't. And depending on the species of bird, it might have different uses. There are birds, there was a 2016 study about frigate birds that have to fly very long distances over 10 days. And this study found that over the course of their journey, if they want to sleep, they'll put half their brain to sleep and then they'll fly in a circle. And what's cool is because all the wiring in our brains is all crossed and weird, right? Like when they put the left side of their brain to sleep, it's their right eye that they close, but their left eye stays open.
Yeah.
And then they fly in a circle, and that eye can watch out for predators or direction that the rest of the flock is going, stuff like that, while they make this little loop. But then other birds, like cockatiels or ducks or even penguins, they might sleep in like a big group, wherever it is, but on the ground, not flying along.
Yeah.
And the birds toward the middle of that group can sleep with both of their hemispheres of their brains asleep at the same time. But the ones on the outside of the group tend to leave one eye open as kind of like sentry birds for the rest of the group.
Yeah.
And they don't apparently sleep as well. So they actually trade off responsibilities like over different nights. Like, oh man, I had sentry duty the other night. I'm beat.
Oh
like,
man,
Carl, you mind taking my place?
Yeah, I slept so good last night. I was like right in the middle.
I was the most safest bird of them all. I slept so good.
Great. I'll go ahead and sentry today. I'll sentry today.
There's this really haggard bird.
He just takes
feathers are all ruffled.
A big old penguin flipper, and he just pats him on the back, and he's like, "I got you, buddy."
He's got like bloodshot eyes and a huge mug of coffee.
But first, coffee.
Oh man, I slept great. What about you, Carl? Oh, how did I sleep? I was watching for leopard seals the whole night.
You got 40 winks. I only got 4.
Which lets me do what I am always trying to do and bring up the Philadelphia Flyers mascot, Gritty.
Oh God, where are we going with this, Julian?
Okay, so for non-Americans and people who don't care about
one eye
closed? Yes. No, it's not that. So Gritty first came onto the scene in 2018, and he introduced himself with a tweet, like a picture of himself saying hi. Oh, I should give context for non-Americans and non-hockey fans, even though I do think Gritty has transcended
somewhat, but still
professional sport fandom. In the state of Pennsylvania, there's a hockey team, the Philadelphia Flyers, and they haven't had a mascot for like almost 60 years. And finally, they created one, and rather than being anything, concrete, like the Pittsburgh Penguins mascot is a penguin.
Right. Most of the mascots that they have are like either related to the city they're in or something related to the team name because it's an animal.
Right, exactly.
Or like a person or something.
The Pittsburgh Penguin, by the way, is iceberg, but spelled like berg, like Pittsburgh. B-U-R-G-H.
I'm not going to comment because
I think that's
the Penguins
pretty good.
Are
okay,
awful.
I think that's pretty. Anyway, so Gritty though is an orange ball of madness.
Yeah,
just like a crazed Muppet, basically.
A Muppet meth head.
Yeah, exactly.
Really upset.
Exactly. When Sesame Street went downhill, when the neighborhood...
In the 1980s. It's a really rough time in the late 80s.
Got hit hard. Basically, Gritty is the product of that. Okay, so Gritty introduced himself with a tweet, and the rival Pittsburgh Penguins, they're on the other side of the state, they just quote retweeted it, just saying, LOL, okay. Like a very innocuous kind of throwing shade. To which the Gritty Twitter responded with the completely unhinged reply, sleep with one eye open tonight, bird. And I don't know why, but that's been in my hippocampus for a long time. I think about it a lot. And then I just learned that penguins do sleep with one eye open.
Yeah.
Do you think the Gritty Twitter account knew? Do you think Gritty knew?
I feel like we gotta find out.
I have to know.
It's this when we get to our 100th episode or 50th episode or something. We gotta figure this out. Somebody reach out to Gritty. Let's find out. Tag us.
So anyway, it's not just birds, though, that can sleep half a brain at a time. There's also mammals that do it, particularly, this probably won't surprise you when you think about it, but aquatic mammals.
Yeah.
So cetaceans, that's whales, dolphins, porpoises, they all sleep basically one half a brain at a time. But they also don't go into REM sleep.
Oh,
ever.
Is that sad? Is it good?
I They seem to be doing fine.
I guess they're
I
fine,
don't know,
yeah.
but oh my gosh, dolphins don't dream. Dolphins don't have dreams. There is something depressing about that, isn't it?
You understand?
Like, you think of dolphins as these joyful, fun creatures,
Right.
and it's like they have no dreams. But yeah, they'll sleep half a brain at a time because they're air-breathing mammals that live in water. So they keep half a brain active to help them regulate their temperature and to help bring them up to the surface when they need to breathe again. They'll also sleep when they're in pods and they're traveling along and half asleep. They will keep their eye open on the same side as another dolphin has an eye open, and they'll maintain like eye contact.
Mhm.
And if they switch sides, they'll switch the half of their brain that's asleep so the other eye can open.
And what would that feel like, having half your brain be asleep? I feel like it'd be awesome. I feel like it'd feel really great. Just be like, oh, man.
Yeah.
Oh,
Hold on, I'm just getting some shut-eye,
man,
singular.
this show is the perfect show to watch. It's like a whole different kind of cozy television. It's a whole different thing. Oh, man, this baking championship sure is cool. I do not care at all.
Yeah. If you've just got something on your like show queue that you've got to get through, but you don't really care that much. Yeah, that'd be nice.
It'd be nice.
There are other aquatic mammals that do it. Fur seals, for example, can also sleep half a brain at a time, but they do that more when they're actually in the water. And so just like the frigate birds, they'll basically keep themselves, swimming around with like one fin, and they'll keep an eye open for predators. But fur seals, when they're on land and sleeping, they'll sleep with both hemispheres at the same time, and they'll have more REM sleep during that time. Put all this together, and I think what I'm getting at basically is there's not enough research to say if other animals sleepwalk as a disorder in the same way that we do.
Yeah.
At least I couldn't find it. But there's plenty of research that animals, air quotes, sleepwalk as an adaptation. And I think that's really cool. End of story. Thank you. But yeah, thank you, Henry. And thanks, Becca, for sending in Henry's question. I hope that was a satisfying answer, at least to some degree.
Yep.
And yeah, if you ever, like I said, want to add to that body of research, it's
That's right.
something that you maybe can do one day.
Don't sleep on it.
Perfect. All right. That's a button. We'll put a button on that. And with that, we will take a break. When we come back, Trace's question.
Julian, give me your best dinosaur roar.
Oh, God, an asteroid! It's horrible!
Wow, that was not where I expected that to go. We're popping in before the show to tell you about I Know Dino. It's a dinosaur podcast.
We think of those dinosaurs being this thing that's been dead for tens of millions of years. Even so, studying dinosaurs can still teach us stuff that is relevant to the world today.
Yeah, like climate models to help us understand global warming.
Migration patterns of dinosaur lineages, they tell us about Earth's changing continents.
We can also study dinosaur diets, what plants lived then and maybe what animals and how they interact.
And, this is super cool, many dinosaur injuries, paleopathologies, they're the first known occurrences of diseases.
And they talk about all this kind of stuff on I Know Dino. It comes out every week with new dinosaur stories that you're not going to hear anywhere else. Like, I hadn't heard of a lot of these, which is pretty cool.
You can find I Know Dino on Apple Podcasts, Spotify, wherever podcasts are. And if you found us, you can probably find them. Go check them out. Hello and welcome back. I hope you had a quick power nap during that. I mean, how long are our breaks?
I don't know. Depends on the break.
You'd need like the penguin sleep method of 9 seconds of REM and then, you're back.
Yeah.
I'm here.
Maybe someday when we have sponsors, that'll change. Right now.
Yeah. Go. They shouldn't call it a cat nap. It should be a penguin nap.
Oh.
Go take a quick penguin nap.
Yeah.
Come on back.
Shut off your brain. Come back. It's nice.
Trace, what did you tackle this week?
Oh, this week was a big one. Okay. So this week we have a question from Rowan in Australia.
Oh.
And he says, we know that there is a level of G-force that will outright kill a human, but is not enough to kill smaller animals like squirrels. So he wondered, what animal would survive a catapult, explosion, or spin launch to space? Could any?
Wait. Just point of clarification. Catapult into space?
Yep.
Okay.
Yeah,
It's not like separate thought, like being catapulted, being exploded, and then being spun launched to space.
all on the same day.
Like,
That would be a rough day.
all of
That would
these.
be a really tough day.
Okay.
So, Rowan, I really love the question. Obviously, I picked it. I was really excited about it. At the same time, though, I just want to point out, you sent me a college word problem. Am I doing your homework? Did you just give me your physics homework, Rowan?
This is a master's thesis you're working on.
What is this? You're asking me 3 different launch systems, and then to determine which animals could survive with G-force sensitivity with modifications to body plan and so on. If using a single force application like a catapult, explosion, or spin launch system, what is the largest animal that could make it to space just from inertial force reaching escape velocity? Of course, that force is applied over time, but it's not continuous after leaving launch system, so the force has to be imparted before or immediately upon leaving the ground, so not a rocket, laser, or force booster. Rowan, you gave me your physics homework.
So not a rocket.
Not a rocket. That
Okay,
is
I was
a
I
key
was going to
point.
cheat and be like, a rocket is just a controlled, pointed explosion.
I agree with you.
Right?
Yes.
But no, Rowan wants one big kaboom to launch something
Yes.
into orbit.
That's right. They say specifically space. So I wanted to be specific and say, we're talking about the Kármán line, essentially, the internationally recognized boundary between not space and space. It's about 100 kilometers. So it's not about. It is 100 kilometers or 62 freedom miles. And so this question is asking me to do multiple launch system math to calculate total force of acceleration depending on different mass payloads to a transition point between, airfoil flight and rocket flight. Also, you have to ignore the mass of the capsule required because the capsules don't exist yet, or assume them, and then also assume air resistance and drag. So this is definitely like a thesis problem.
All right, yeah, go ahead.
And normally we
do rocket science.
So
go.
The reason I picked it is because I'm not going to do any of that math.
Oh, you tease.
I'm not going to do it. But what I am going to talk about is crazy wild space launch systems, because there are so many. So what Rowan wanted to know is, could anything survive a crazy wild space launch system? And there are several, and make it to space. Getting to space is like notoriously difficult. We know this. It's something that is actually a problem with NASA's system, not because NASA is a problem, but because they're so good at getting people to space that it became routine. It became boring. And yes, they have had some terrible disasters, Challenger, Columbia, Apollo 1, a variety of problems. But most of their launches go well, and they do these incredible things that are inspirational to people all over the world, and they do it in what seems like easily, almost. Not really, because it's a lot of work with thousands upon thousands of people doing it. But getting to space is notoriously difficult, and because of that, we have all of these different ideas of how to get to space, but we mostly use rocket. And the reason we use rockets is because it's not because, again, rockets are easy, but because getting to space is so hard that rockets are actually the easiest way to get us there.
All of the ways.
Not only did we have to invent a rocket, then we had to have that, as Julian so eloquently put it, a controlled, directed explosion that we could get you from the ground out into space.
Yes. And it's especially if you're going farther, right, like the moon, it's so insane to think about. Like, I love, you and I both have the Lego Saturn V set.
Right
I
there.
can even see it
right there
behind you in our video call here. And like, it's so crazy to think the scale of this thing, right? Because it's like the Saturn rocket set is like a meter tall, and it's a 1/100th size scale.
Yeah.
And like, when you look at like it's like one little tiny Lego brick. It's like a single brick high. And it's like, that's the capsule the astronauts were in. And everything else essentially is fuel.
Yeah. Just empty with fuel and rocket engines.
Yeah, it's just a lot of hydrogen, oxygen, and then kerosene for my Apollo space flight program nerds.
What up?
First stage was kerosene.
That's right.
Okay.
So basically, these kind of things are like a Saturn V is classified as a super heavy lift rocket. And there are all sorts of different classifications. Most of the ones that we're talking about today aren't going to be super heavy lift. And super heavy lift can lift big stuff, like the mass of the Statue of Liberty, just the statue. That could be lifted by something like a Saturn V, but just the statue, not the base. Still quite large, quite heavy, even though it's hollow. 20 times an elephant basically is how much it could lift.
Thank you.
Yeah, just to give you a little context.
I was wondering when we'd get to the measurement.
You're welcome.
Conversion.
The thing is, the rockets are out. Rowan says no rocket. And so I do want to talk a little bit about some of the other things that we want to try as humans or that we brainstorm. I do want to say just off the top, when I was 10, I had a notebook. And in that notebook, I swear it was pencil. I would keep it on me and I would write down invention ideas. Some of these are like that. They are just like, these are ideas. They will probably never happen. Even if you do all of the thinking through all the little then we could do this and then we could do that and it would be great. And we could do, and then you just have this little cable right here and it would lift this much. And it's like, yeah, these are just dreams, mostly. Some of them have been built, but a lot of them are just like, maybe someday if we find the right material, we could build this. So I also want to mention a pet peeve of mine when it comes to any of this rocket stuff and any of this getting to space stuff is people who say, this device, lately it's been Starship, can do this. And it's like, no, it's not. It can't do it. We don't know if it can. We think it might. It probably will, but it hasn't done it yet, and we haven't been able to actually succeed, and thus it cannot do it.
The goal of this device is to do this.
Right.
But
and I find specifically with Starship, but also many of the devices like this, space elevators and things that we're going to talk about, it's better to be cautiously optimistic than to say a space elevator can lift. And it's like, no. It probably doesn't exist.
I mean, especially you and I spent a lot of time, making content for social media platforms, and they thrive on short, very light in details, videos about some wild idea postured as a thing that's going to exist, a year from now. Right.
Yeah.
There's so many things that pop up all the time, and then people get really excited about them because, of course, they're presented in a really snappy, 5-minute package. They look really cool.
Yeah.
But it's the technical details of this are a lot more complex. And a lot of these promises that you see in these little videos and whatnot is just some marketing video or some outlet that wants to publish some content for today to drive some clicks and make some money,
Yep.
But it's very hard to find reliable, technically sound, future solutions to space travel that you can really put any sort of stock in.
Yeah. 100% totally agree. So with that, let's talk about the 3 different ways that we can really get to space, right? There's from the ground, which is, you're shooting, or you're flinging, or you're exploding things. There's from the air, which is pretty common, where we're seeing things lifted up with some other known technology, a balloon or an airplane. And then there's from space, where we pull it up from space, something already up there, we swing it up, or something like that, where you're already in space and you're drawing something up to space where you already are. So those are really...
I'm just imagining a satellite with a winch lowering a long 200-mile long hook.
Yeah, just lower down.
And then people being on the ground all right, here it comes.
Jump.
It's like the latest food resupply for the astronauts on the ISS.
It's a basket.
It's just this hook.
It's a basket with a pulley and a rope. And they're just lowering it down.
Yeah, it's a picnic basket. And there's 8,000 kilometer an hour hook.
Honestly, yeah, that is one of the ideas. We're gonna get to it.
No.
But let's start with the cool stuff, the stuff that I think Rowan was thinking of when they wrote this question, and that is the stuff from the ground. So some of the earliest systems for getting things into space is pretty simple, right? Think about it. You're a person in the 19th century, and you're like, I want to go to the moon. What technology is probably the technology you're thinking that's going to get you there?
Oh, you say 19th century go to the moon. I think a big cannon.
That's right. And so we have those things. They are called Project HARP. They were built in the 1950s, and it's essentially a giant cannon.
Just a great big flipping cannon.
That's right. They actually built one in Barbados, and they tried it out to see if it would work. You can go online and see rusty pictures of the barrel that is still apparently there in Barbados. In fact, the reason I picked the 19th century, one of the first films ever made is From the Earth to the Moon. And it is basically that. It's this idea that these people, they get in a giant ballistic bullet, they locked into a cannon, they shoot at the moon, and then they walk around and meet people who live on the moon when they get there. The Project HARP was actually, again, built in the 50s. It was designed by a controversial ballistic engineer, says the source that I was reading on NASA. His name was Gerald Bull, and he used an oversized gun to throw a subdimensional vehicle mounted in a shoe, essentially a way to get it there. There are a lot of different design iterations of Project HARP. Again, they built a cannon in Barbados. The reason they picked Barbados is so that the projectiles would fall into the ocean if they failed to get to orbit. In November of 1966, the Yuma version of Project HARP was able to send a 180 kilogram Martlet 2 projectile to space. They got it there.
Whoa.
It was a muzzle velocity of 2,100 meters per second. And it was in space very briefly, reaching 180 kilometers, about 110 miles, and then fell back down to Earth. It all sounds very cool. But if you think about this, is this viable for something like Rowan? With their question of what could survive this? So that's where we get to, I did do a little bit of the math, we get to G-forces. So G-forces aren't actually forces. G-forces are a way to describe acceleration. And so a G-force is essentially an acceleration. All physicists would just call it acceleration. If you're slowing down, you're speeding up. Either way, you're changing your acceleration. And so you have 0 all the way up to, infinite acceleration. And the change over time is what gives you a G-force.
Right. So, you and I here on Earth, we experience the force of gravity, and it pulls us down towards the center of the Earth at a rate of 9.8
meters per second
squared. Yeah, exactly. And that is, just to make things simple, 1 G.
Yes.
Right?
Right.
But if you are, say, on a roller coaster and you get accelerated, you're going through a loop or whatever, and you're getting pressed harder into your seat. If you experience you're getting pressed into your seat at a rate of 19.6 meters per second squared, so twice the rate of gravity, that's 2 Gs. Right.
When I was in 8th grade, we did a physics trip to Cedar Point, where we, in science class, we all built using a lead weight and a spring. We calibrated 1 G in a plastic tube, and then we marked 2 Gs, 3 Gs. We calculated it out. And then we went on roller coasters to determine the G rating of the roller coaster and then marked it down. It was really awesome. A great science trip.
That's so cool.
It was really fun.
That is so cool.
Yeah.
Yeah. But for context, because I have to bring up aviation.
Yes.
For a World War II fighter pilot, 6 Gs is kind of the max of what they could take before passing out.
Yeah.
And modern fighter pilots, they can go all the way up to 9 Gs, but you need suits because the force that's being put on your body, it's being applied to all the things inside of it too, like your blood, and it causes the blood to leave your brain and go into your legs. So they wear these special air-inflated suits that squeeze their legs and push the blood back into their brain so they don't pass out above 6 Gs.
I have worn them. When I flew in the F-18, I had to wear it. Very uncomfortable. The squeezing, so it's actually attached to the plane. So you plug in, and so the plane is measuring the G-forces and then squeezing the blood out of your legs relative to how many G-forces you're experiencing in that moment. And so it's very uncomfortable. You can also train your body. You can bear down or whatever, basically just squeeze your muscles to try and keep the blood where it's supposed to be. But yeah, you're totally right. You have these big suits, and I'm sorry to bring it up. I know it makes you sad that you didn't get to wear them.
It was before anybody at Discovery knew that I was a big aviation nerd. I just started, but I'm so sad. One day.
But it was very cool.
But yeah, they need these, though, for these high G maneuvers because planes are so much faster now.
Yep.
So when they turn, the G-forces are a lot higher.
And I like that you bring up planes, too, because the thing about G-force, again, it isn't a force. It's a measure of acceleration. So if I'm on an airplane and that airplane is, say, a commercial flight, maybe I'm at 30,000 feet or whatever, I'm going 500 miles an hour. Sorry, miles. Whatever that is.
500 knots.
Yeah.
We talked about this.
About 500 knots, whatever that means. I don't feel like I can bounce a ball. I can throw a ball back and forth. I can throw it up in the air and catch it. I can walk around and spin in a circle. And I don't feel like I'm spinning in a circle at 500 knots. I feel like I'm not moving at all because
Right,
G-force is a measure of the change.
Change in velocity, which is acceleration.
And so what we do know from researching G-forces, specifically in aviation and in the space programs all over the world, is that 50 to 75 Gs will kill a person. A human can survive at about 50 Gs. It will kill a child or, a woman, they said, up to 75 for men. I don't think that actually is probably true. It probably has more to do with the person than their organs, but that's fine. Either way.
Yeah.
A study in 2001 in Earth and Planetary Science Letters looked at other things, like, for example, bacteria. And the reason they looked at bacteria, which Rowan does mention, small things like insects survive G-forces more readily. And that is true. And in fact, bacteria were put into an ultracentrifuge at 100,000 RPM. That is equal to the acceleration of 4.27 million meters per second squared. So very high acceleration. And after 72 hours at that acceleration, they were considered inactivated. Basically, they were dead.
They got spun to death.
They got spun to death. However, they also loaded them into projectiles and fired them at targets. And those were very low-level projectiles. They were firing like air rifles, essentially.
Did these researchers just have a grudge against this bacteria?
They really hated microbes,
Was
bro.
it E. coli and they had gotten like food poisoning earlier and they were like, oh, that's it. I'm going to have my revenge.
Do some research. Take it out. You're never going to give me diarrhea again. Except for they probably would.
Oh, my God.
And they were firing them in these projectiles at about 100 to 300 meters per second. And their survival rates were between 40 and 100%. It just depended on the bacteria and I'm sure the scenario. So either way, the idea behind this study was for panspermia. If you know what that is, it basically means something hits a planet that has life on it and the bacteria or microbes on that planet get thrown into space. Could they survive that? The only way we would know if panspermia is possible to know if the microbes could survive being thrown off their planet at a ridiculously high accelerated rate. And then once they're in space, that would be a different study. Can they survive the harsh environment of space to get somewhere else? If they can't survive that initial explosion, then there's no reason to even think about it. So that's where this study came from. And they found that some actually could, even at ridiculous, like 4.27 million meters per second squared. Again, gravity of 1G is 9.8. So like this is a ridiculously high G forces, and
yeah, it's higher than like 9 Gs.
Yeah,
like they think fighter pilots are a bunch of wusses,
and they could survive for days at that acceleration.
They're comfortable.
They were cool.
They're just eating some contaminated lettuce.
So this is why it's important to do all of these different tests. Let's come back to some ridiculous systems. So let me bring it back to Project HARP. Is this viable for Rowan? An estimated muzzle velocity of 2.14 kilometers per second, or about 4,800 miles an hour, about 1.3 miles per second, is too much acceleration for things to live. You're not going to get a human, definitely. You could get bacteria to live on this stuff, but they're asking about stuff that's bigger, a squirrel or, something like that. No, squirrel's not going to survive being shot out of a cannon at 7,700 kilometers an hour. It's just not going to happen. So let's go to another crazy launch system, the mass driver or the railgun. They're
fun.
Two similar but very different, also ballistic ideas. A railgun is electromagnetic rails that pull, similar to like a maglev, a projectile, usually a very small one, and accelerate it at a ridiculous rate so that it can shoot through stuff. You see it in sci-fi all the time. Mass driver is a similar idea, but instead of rails, it's coils. Again, it doesn't have to use electromagnetism, but that's the most common way. And these were thought up and proposed even as far back as the early 20th century. They're appear in sci-fi books by Arthur C. Clarke and Robert Heinlein and all sorts of others. So the mass driver, they actually built one. It was invented by Gerard O'Neill in the 1970s. It's basically a bucket of stuff, not really a bucket, but like a projectile wrapped in a coil. And there are magnetic coils in a really long tube, again, like a maglev train, where if you don't know how a magnetic levitation train works, there are magnets in the ground or the track, and then they essentially are turning on the one in front of the train to pull it a little bit, and then they turn on the one in front of that to pull it a little bit, and they turn on the one in front of that. And they do that fast enough that they're slowly accelerating the train. When they want to slow it down, they do the opposite. They repel it a little bit, and slow it down. So in this case, you're doing that with coils and a really long tube, and you're accelerating this mass by pulling it through it with magnets. By the end of the 1970s, they had improved this mass driver design, but they found that the acceleration was around 500 Gs.
Jeez.
Yeah. It was a lot. It was a lot. And they also said these probably would not work on Earth. Any wonder why that might be, Julian?
Okay. Air resistance?
Yeah, that's right.
Really?
You want to expand
much?
on that? Yeah, so these were thought of as something that you would do on the moon. You would build a really, really long maglev track, and you could shoot something from the moon, to wherever you wanted it.
Yeah, to send
go
a
back
message
to
to the
Earth
other
or
planets.
somewhere else. Yeah.
Look out, solar system, we're armed now.
Yeah. But the air resistance on Earth would make this pretty tough.
Something so American about putting a big gun on the moon for reasons.
Yeah, for cargo, obviously. For cargo, Julian. This has to do with that acceleration that we're talking about, this G-forces. At 500 Gs is a lot. The thing is, with something like a mass driver, you could accelerate it over a long distance, but the longer you use to accelerate it, like let's say you're trying to build it so something living can survive in it, that's going to require a really, really long track and very slow acceleration. Remember, at 50, we're dead. So this is 10 times more than that. So we have to slowly accelerate over a really long distance in order to get to a high rate of speed before we throw it out into space.
Yeah. But
if it's dead or solid, you can do that really, really fast.
The issue I see with as the way Rowan asked this question is that 2 of the 3 methods he described would involve a very brief window to accelerate the thing to, escape velocity or orbital velocity or whatever. And the shorter that window is, by definition, the higher the acceleration must be.
Exactly. Yeah. Just because of the way acceleration works, that delta is important and time is important. Right. So the shorter the amount of time you have to accelerate something to escape velocity, which is 11 kilometers per second, by the way. I know I hadn't mentioned that yet. Sorry. So 11 kilometers per second is our goal. You have to accelerate to 11 kilometers per second or 11,000 meters per second really fast.
Yeah, in a very short amount of time. So yeah, the average acceleration is take 0, your starting velocity.
You're not moving at all.
Take the one you want to end up with, add them together, divide by time.
Yeah. And the gravitational constant of wherever you're shooting. And so, yeah, you're talking about if you're going from 0 kilometers per second to 11 kilometers per second in a single explosion, so let's say a millisecond, that is 1,000,000 Gs, which is going to even harm a lot of bacteria. And so going from 0 to 300 meters per second, like in that bacterial experiment that could harm up to 60% of what they were finding, that was 670 miles an hour. That's relatively speaking very, very slow.
Oh, yeah. Walking's practically.
And so, yeah, almost. Yeah, sure. You are a fast walker.
Yeah.
So let's move on to something that has a little more of this slow acceleration. Obviously, big explosive guns aren't going to work. It's just too much acceleration all at once. So then we get to something like the Lofstrom loop or the launch loop. Did you know anything about this? Have you seen this before?
No, this is news to me.
This was new to me as well, and I really think it's very cool. It was come up with by Keith Lofstrom. I actually found a presentation that Keith did because I was in a forum reading about this, and they said, and Keith, he commented on the previous post, so I started a new one so that we could talk about it. And I was like, wait a minute, this guy's alive and talking about it? That's cool. So I found a presentation he did on it, and it was presented in 1983, and essentially it's a vacuum tube filled with moving magnetic iron. Now, the reason that's a tube filled with iron that is moving, the Keith used the analogy of a hose. So you have a hose filled with water in a garden hose, very high pressure. You have a very high pressure hose and you point it up into the sky, like in your backyard. It's going to make an arc.
Right.
Now, if you have a higher and higher pressure hose, eventually you can make an arc that would be so strong, the water pressure would be so strong and the arc would be just right so that you could actually miss the curvature of the Earth.
Right.
You're shooting into orbit using this. Now, water is not going to do that. However, if you had a air-sealed tube filled with moving iron, then used, again, magnetic principles to move the iron at a speed that would be so fast that you're essentially using the iron to hold up a track. And that track only has to be, 5 centimeters or something, he said in his designs. But instead of spraying water and having it come down in an arc, you're spraying it so fast and you're spraying iron that you're doing it through 2,000 kilometers of track. And that would be able to essentially lift something into space. The mass stream, again, that iron that you're moving through this vacuum tube is running at 14 kilometers per second. So it's running very fast. You could not do that in an air environment. And aerodynamically shaped launch vehicles would be going up this track. And he says that they could do 5,000 kilograms riding. Like, that's a really high amount of mass. And it would basically, I picture it because we're sort of getting into the weeds, but it's like a roller coaster track.
It's what it
Basically,
sounds like.
It's a really big roller coaster. It's 80 kilometers of roller coaster track in terms of elevation. And then from there, you would continue into orbit. At that point, you're very close to the carbon line. You're above most of the atmosphere. You just kind of have a rocket that would take you the rest of the way.
Okay.
But you're on a really big roller coaster.
So this is what I'm picturing it is like, basically when this launch loop system is turned off, it's like kind of like a deflated tube man. Like those car sales lot tube men guys. And then you turn it in and these tube men billow up, but they're full of moving iron, which is therefore able to support something heavy like a rail.
Yes.
And then you just like take something on a cart on this rail up into space above the atmosphere. And from there you launch.
Yes.
So it's the wacky arm
that is the right
waving
reaction.
tube man space launch delivery
launch
system.
Yes. It is a high pressure garden hose filled with iron, anchored at both ends so that the pressure in the hose of the moving iron is what keeps it up. Of course, it has lateral stability to worry about, so that he's designed this whole system. This has to be built, by the way, in the ocean at the equator off the coast of South America. It would cost, like, he thinks $10 billion to build, and I laughed. This would cost $1 trillion easily to build. And he said it would have to have electricity constantly moving the iron all the time. But if that was the case, then you could launch all sorts of things very easily because it would be constantly moving. So you're just kind of riding up the magnetic track into space. And he says that it would be, you could rise at like 3G. 3G is like the space shuttle launch.
Oh, so gentle.
Yeah, relatively gentle, even though, 3G, you're 200 pounds a person. Now you feel like you're 600. That's not a ridiculous amount of G. So you could still lift up your arm. It would be hard, but you'd be like, oh, wow, it would be fine. So this is a pretty interesting system, but it is one of those in the wacky, super like out there because it would be so expensive to build. It's so big, 2,000 kilometer loop track with moving iron in it, constantly powered. You could never turn it off. He's like, well, if an airplane hit it, then it would fall back into the ocean and you could recover it and just put it back up again. And I was just like, oh my God.
I don't think you're going to get beyond the PR disaster of an airplane hit your ridiculously over elaborate launch system when rockets are already a thing, as we have discussed. I think, you know what this would be good for, though? Bringing pizza into space because it's so pie in the sky. It's ridiculous.
Wow. Did you write that in advance?
No. No. Just off the top of my dome.
That was pretty good. That's pretty good. Okay, so let's move on to another crazy one. So even though, yes, I want to acknowledge Rowan's question. So yes, this launch system, with the material that we have now, it could be built. The thing is, you'd have to anchor it to the ocean floor off of the coast of Ecuador, and it would be, again, 2,000 kilometers long and go 80 kilometers into the sky. That's wild.
Right.
On so many levels.
When rockets that can already safely carry humans to space exist.
Right. I think the benefit of something like this is similar to the benefit of some of the other stuff I'm about to talk about in pulling up from space or like space elevators, is that it could constantly be taking things up into space. Millions and millions of kilograms per year could go into space, which right now that would be very, very difficult. And Keith is clearly very passionate about it. I'm very excited for them. They are clearly not an economist or in politics because they're like, yeah, you just build it. It would cost like $10 billion to build it. It would make all its money back really quick. And it's like, this would take a century to build.
Oh, the shipping lanes it would interfere with?
The political implications, the air implications, the ocean implications, the pollution implications of having all of this stuff being built. He's like, you could build multiple of them all along the equator through this part. And it's like, oh my gosh, this is the theme of my answer here is optimism. The key here is optimism. Okay, so let's move on. We're running out of time. So centrifugal launchers, they exist now. They already exist. So a centrifugal launcher would be like a carnival ride. You're spinning in a circle on an arm or something. You have a counterweight. And then at some point, a computer releases the payload and you fly into space. The problem with a centrifugal launcher is this is the exact same amount of acceleration. It's just spread over a slightly longer time. And as soon as you hit the air, you're going to have air resistance. So even if you're accelerating within a vacuum, you're going to hit the air. So I looked up a nice write-up on Wired where a physicist did the math, and it was fascinating. And he wrote, if you were inside one of these, hitting the air would likely kill you.
Yeah, right? Because it's going to be a very sudden deceleration, which is just G-forces in the other direction.
Right. Now, that said, I want to talk through what this is. Okay, so this is basically a hammer throw, if you watch the Olympics, into space. And they have one. There's a company called Spin Launch, which is trying to make one. They haven't built a full-size one yet. But the idea is it's a 90-meter or about 300-foot arm. It has a counterweight on it. It spins in a vacuum chamber, and it slowly increases to about 4,700 miles an hour, 7,500 kilometers an hour, over about an hour and a half. So you're slowly accelerating, and at that point, it's spinning so fast that the mass on the end of the arm is feeling so much lateral force that it would be akin to holding up a Saturn V with just the arm of this thing. At that point, the computer would release the payload through an airless tube. They don't know the length of the tube, and it bursts through some kind of membrane. Don't know what that would be made of to somehow be both pierceable and also maintain a near vacuum. And then it would ideally reach about 61 kilometers into the sky, which is right below, well, not quite to the carbon line, a little more than halfway. And then it would take a rocket the rest of the way into space. They say like a 10-second burn would get them into space. It would be 100 kilograms of payload. Either way, though, Big Think wrote, it has wicked G-forces, 10,000 times the force of gravity, so 10,000 Gs, enough to tear skin and muscle off of a human being.
So
yikes.
So bad.
So bad.
I think I need my skin to live. I haven't tested it, but I'm pretty sure.
Like to keep my skin, please. Thank you. Not only would this have ridiculous deceleration as soon as it does hit air, because it is, even unless you have a tube that's so long that it goes above a lot of the atmosphere, or you put it on top of a mountain or something, so it's already above a lot of the atmosphere. Either way, it's going to have massive deceleration, and then it's going to need to be somewhere not dangerous. So you need a mountaintop high above the atmosphere on an island, like, for example, Hawaii. So you have to ship your spacecraft to Hawaii, put it on top of a mountain, spin it, and throw it into space. Probably not going to have a lot of really living things doing this process. So sorry, Rowan, on that one.
Yeah. So my thought was, part of the consideration is you need to account like the direction that the acceleration is being felt, right? If we go back to our Saturn V rocket, those three little astronauts in the capsule at the point of it, they're lying on their back when they're in the launch position, right?
Yes.
Same for shuttle astronauts.
Really great point. Love that.
And that has benefits for withstanding G-forces. Modern fighter jets, the F-16, the seat is reclined at 60 degrees, so you don't get that full brunt of the G-force, right? It's like it's a trigonometry question, basically, right? But but the angle makes it so, you don't experience it as much. You can withstand higher. If we think of the spin launch system, right, it's accelerating this object in that circular path as it spins up, but it's also going to experience more and more centrifugal force. And we talked about this on the last episode, I know. Centrifugal force, not real. It's not a real force. But there's not actually something pushing you to like the outside of a centrifuge or the merry-go-round or whatever. It feels that way to you, but really what's happening is your body wants to continue off of this circular spinning object in a straight line. So that turn to keep you going in a circle, you feel that as a force, because velocity is not just speed, but also traveling in a direction. So if you change direction, by definition, you are changing velocity. And therefore accelerating.
Right.
Okay.
And so when you're on the spinning spaceship ride in your carnival, the wall is pushing you in a direction as you're pushing against it, Newton's whatever law. And like then the velocity that you're experiencing is moving.
Right.
And
so in this spin launch system, as it accelerates, as it spins around, you're going to have it so it can withstand being, sped up as it goes in the circle and pushed against that wall. And then when it comes out of the tube and hits the air, then the frontal part of the projectile is also going to need to be braced to withstand the sudden deceleration of punching into a mass of air all of a sudden.
Yes.
So,
this is pretty serious.
You're going to get hit literally from 3 of 4 sides possible.
Right. And so microbes, maybe squirrels, probably not. Mm-hmm. It's going to be a real messy projectile
squirrels
on the inside. So this is basically not that different from the mass driver railgun ballistic systems. It's definitely more akin to that than to something like the launch loop, even though it does feel different because we're like, oh, we're spinning it and we're accelerating very slowly. And it's like, yes, but then as soon as we let go, it's ballistic. And so then our acceleration may have been constant the moment we let it go. It might be, then we finished accelerating. Now we're decelerating. And then over the air resistance, we got a problem there. Okay, so we're done. These are all of the major ways that we're thinking about getting things from the ground into space. So the next thing we would do is go into the air. We're going to go way up high and we're going to do an alto launch, which is an air launch to orbit. Virgin Galactic already does this. There are lots of different plans on how to do this. You essentially have an airplane or some other flying contraption with a rocket on it. An alto launch is how we would do horizontal takeoffs, carry a satellite into a high-level airfoil area, so still below the Kármán line, you're not in space. And then you would release it, say a Pegasus rocket, and it would go up into space. It can carry, a very light payload relative to a traditional rocket because it has to be lifted in 2 different ways. Mm-hmm. But it does have a lower cost because airfoils are relatively cheap.
Yeah.
And that makes it great.
That thick part of the atmosphere down low is an issue for rockets. You also, part of the benefit of having multi-stage rockets is you can optimize the rocket for the ambient pressure, right?
Yeah.
So at lower levels, and it all comes down to how the nozzle, like basically how big the nozzle is. In space, like they're great old big nozzles, and then down here on the ground, they're much, much smaller nozzles. And it has to do with being more efficient at different altitudes. So you could have a ship that's more optimized for higher altitude. But it's funny because if you take it up on an airplane, like the X-15 rocket plane from like the 50s and 60s was one of the first craft to go past the Kármán line. And it was carried up on like a B-52. And that still only buys you, right, if we were trying to get over 100 kilometers up, starting from a B-52 or something like that only really buys you like 16 kilometers in altitude, like 50,000 feet.
Right. I mean, it's like the reason the Kármán line is there, it's 62 miles, by the way, for our American friends. The Kármán line is there because it's like when you absolutely have to switch to rockets. You can't use airfoils anymore. There's just not enough air. The thing is, most of the time, most of the airfoils we use, you're above a lot of the atmosphere, even in an airplane. You're above most of the atmosphere. You can say that most of the time. As you're rising up, you're always above a lot of atmosphere, more than you were, because, there's a lot of air near the ground. That's just gravity. And so this is helpful. There's also raccoons, which are just a fun, cute little name for launching from a balloon, a raccoon.
Oh.
So there's a really excellent D-News video with our friend Amy Shira-Title, who she talked all about this. It's a concept that originated in the 1940s. It was for high altitude atmospheric science. You have a big balloon, just a weather balloon, and you, instead of a payload like science material, you would put a sounding rocket on the bottom, and it would have, like a 25-pound, 11-kilogram payload. Not a huge amount, but you can use that once it goes way up into the atmosphere, like into the stratosphere, they can launch from there. And so you could send instruments 50 miles up into the air or, most of the way to the Kármán line, but still just over halfway, to be honest. So In fact, this was something that James Van Allen used to do, is use raccoons. And then he later had the Van Allen belts named after him because he was doing a bunch of atmospheric science.
That's he's the discoverer of those belts because of probably these experiments. Exactly. So cool.
They used a satellite to discover them, but he was using raccoons to do these high-level atmospheric sciences. So it's pretty cool.
Neat.
So with this, Rowan, I think with a raccoon, you could launch an animal, maybe a small one, because it's really just a rocket. So, but it's a sounding rocket. So we're talking a very small animal, like a mouse, maybe. And it could survive because these aren't going to have a ridiculous G forces. They're going to just do regular old rocket stuff. And so now we're up into the pulling from space. These are my favorite. I'm going to talk about them for the least amount of time because they are all made up. There's the rolling sky hook.
Oh, no.
This is the one we sort of alluded to earlier. The rotating or rolling sky hook is an Earth orbiting cable.
Oh, no.
That is very long.
I was joking.
It's a third of the Earth's diameter long. And it orbits the Earth every 2 hours. And there's, let's just say a hook, but it's probably not a hook. Let's say a hook.
Just a big, rusty...
A picnic basket on the end. And every 20 minutes, this giant cable is rotating and it comes near enough to the surface to put a payload on it. And it is essentially stopping in the air for a second. It's like hovering there. And you put your payload on it as it kind of swings by, like a giant ski lift. And it's constantly spinning, but slowly. So you have about a 1.5 G acceleration once you're on the cable. That's pretty low. And you're on your way to space.
And then you get winched up.
You just get winched up.
Just
and
imagine
similar to
hearing elevator music for 200 miles.
Yeah. So it's a low acceleration, but... All right,
just another 4 hours of this. Crazy weather we're having lately, huh?
Because it only can be like 8 seconds and just has to repeat because, licensing.
Wow. That's my nightmare.
Yeah. So, yeah. And it's not going to have a lot of payload. Because the more payload you have, the heavier the cable would have to be, which means the more mass of it's just everything is wild. On top of that, if your payload is very heavy, it's going to pull the cable because of Newton's laws.
Right.
Even though this is complex orbital mechanics and Newton's laws only you have to get more complicated than that into the calculus. It still is just like a giant spinning cable like in space. So this comes back to my 10-year-old notebook. This is an idea from a 10-year-old's notebook. It's just like, just to put a giant spinny thing. Then there's the space elevator. It's a geostationary satellite that's very heavy with a cable that's attached all the way to the ground. And similar to the loop, something climbs the cable, literally a space elevator. The problem is the mass of the cable for both of these is a huge deal, and what the cable is made of is a huge deal because the forces at either end are going to be wild. And so it's just going to pull through the middle of the cable, and if that thing breaks, we're in trouble. So, Rowan, after all of that, I love the question, but it makes a really huge assumption, but not in physics, really. It's more, the assumption is our knowledge. We don't have materials that can do a lot of these things. We don't have the ability as a species to build a lot of the stuff we're talking about. And so it's just, we do know how to make chemical rockets. And we're even learning still about how to do that well. And it's just like, but to make a cable that can do this, we would need materials that we just don't know how to make. And we would need them on a level of a third of the Earth's diameter, which, think about how hard it was to build a really tall building. And that's nothing relative to that. So it's really interesting to think about it. But it's sort of, when I used to work at Discovery, I met this producer who didn't do a lot of science producing. And he said to me, what's the most surprising thing about this job? The stuff we don't know. We don't know a lot of things. And it's like, yeah, we don't know almost anything. We're still learning a lot. And something else we don't know is the G-forces that will harm animals. The reason I didn't just go do the math, because honestly, we do know that it is an inverse relationship. In a study from 1975, we absolutely know that body weight is inversely related to the threshold G value at which animals are resistant to prolonged acceleration. This is a study from the 70s. They did studies with mice, rats, rabbits, finches, pigeons, and roosters and exposed them to a bunch of different G-forces and inertial forces. And they found that they would harm some of them at different levels. And they made this inverse relationship. But it wasn't like, oh, okay, cool. Now we just know all of the animals that are going to be damaged and in what way, right? We didn't launch animals into space just to find out what was going to happen to them. We mostly wanted to launch animals into space because we couldn't launch humans because it wasn't safe enough. Then once it was safe enough, we were launching the humans, and then we were launching animals again, but for a specific reason, to study how they behaved or how they bred. And again, it was because we wanted to learn more about people. And so we don't just like launch animals to see if we can launch them, although we have launched primates, monkeys, mice, dogs, rabbits, apes, chimps, guinea pigs, cats, frogs, fish, spiders, squid, microbes of all types, wasps, beetles, tortoises, flies, worms, bees, ants, frogs, I already said frogs, crickets, minnows, newts, snails, urchins, moths, brine shrimp, jellyfish, guinea pigs, butterflies, scorpions, and even cockroaches, and even quail eggs, which were fertilized but unhatched, and they hatched in space.
Wow, they were born in space.
Yeah. Cool. And of course, we've launched things like Laika the dog, most famous space animal, R.I.P.
Ham the chimp.
Yeah. Like we've launched all sorts of animals, but most of them were to research what would happen so that we could learn about us. As Chris Hadfield said once in a lecture I attended, the most experimented animal on space is us, the astronauts. Like they're the most experimented on animal in space because every time we're in space, we're learning something new about ourselves and what we do up there. So to wrap this all up, the space shuttle, was about 3 Gs in a launch. The Saturn V was maybe 4 or 5. An elephant is 1,800 kilograms. If you could build a thing that would hold an elephant and put it on top of a Saturn V or into a space shuttle, both of them could probably lift an elephant in terms of its weight. 1,800 kilograms for something that was that big, like a shuttle or a Saturn V, is not actually that much. However, it would be experiencing 5,400 kilograms, and we have no idea what would happen to its brain, its connective tissue, its organs. I attended another lecture of John Glenn and Michael Collins, and they were talking about the EIEO experiment, which is essentially a centrifuge with a capsule on it, and they put an astronaut in it, and then they flip it. So if you turn 180 at a fraction of a second, so if you're accelerating at 10 G and you do 180, now you're accelerating for that fraction of a second at delta 10, like 20, basically. So you go from positive 10 to negative 10.
Jeez.
And that's a 20 G change. And John Glenn said they did that with this specific doctor who was like his friend. And he came out coughing. And they said, oh, well, we're not going to have the astronauts do that because they're too expensive. It's like they're too important. We don't want
doctor.
That. Yeah, that doctor guy, expendable. Turns out that his lungs had crashed into his rib cage and knocked the wind out of him. Essentially. Ouch. Yeah. They figured this out later. And he was talking all about this in this lecture at the Smithsonian. It's super interesting. If you ever can go to these, they're so neat. But like, we only know that because we're like, we have to send these people into space. So we want to like push the limits and see what we can do. So Rowan, I don't know. We don't know. We as a species don't know, except for the animals that I listed. We don't know what a lot of high Gs will do because we don't just like put animals in high Gs to see what would happen.
Yeah.
What we do know is there are a lot of animals that experience a lot of G forces. Everything from insects, because they're very small, experience them differently than larger animals, but larger animals are multicellular and their pieces don't all fit together in the same way. So even though an engineer would just be like, oh, it's a relationship and we can just graph it. And it's like, that's not how bodies are. And
say that to my liver, like
it just doesn't work that way. And so it's really, really cool. And if you want to start launching some animals into space and figuring out how they'll do it,
please don't.
Cool.
Please don't. Please don't.
I wouldn't recommend it.
Please don't start testing on animals with explosives. Please don't. I'm going to put the kibosh on that right now.
Yeah. Don't do it.
Don't do that. Don't do that. Unless you go to school and get a fancy degree and somebody signs off on it.
Launch a space company and then, have a reason.
Become a billionaire and then nobody can stop you. You can launch whatever you want up there.
I think the only thing we do know, Julian, is that a Klingon bird of prey can lift a whole tank filled with whales. And that's pretty awesome.
And those whales, they don't dream of space because they can't.
They can't.
They live it.
Live it.
Well, thank you, Trace.
Thank you. Thank you, Rowan, for asking your question. And thank you all for listening to this nice, not mathy episode of That's Absurd. please elaborate. If you liked these questions, please leave us a review and tell us that you liked these questions and that you want to hear more. And if you have a question and this, prompted any question for you, go down into our show notes and leave us a question and all the different things we're about to list. But just so you know, we can't do this without your help. So thank you so much for those who have submitted questions and for who are listening now and who have left reviews. We read them, we see them, we love them. Thank you so much. Thanks for listening to this episode of That's Absurd. Please elaborate. As always, this show was created and written and produced by me, Trace Dominguez.
And me, Julian-focused.
And it was edited and produced by the wonderful and probably launched into space Kyle Sisk.
Yeah, we haven't heard from him for a while. It's the only explanation. That or he's on vacation.
Oh, well, that would be Occam's razor and more simple. Yeah, you're right.
Yeah. Special thanks to listeners who submitted questions featured in this episode. That would be Rowan and Henry by way of Becca. If you want to leave us a question, go ahead and submit it. You can use the form in our show notes. You can email us at hello@that'sabsurdshow.com. You can visit our website, that'sabsurdshow.com/ask. You can even pick up your handy dandy cellular telephone device and punch in the numbers 302 tape show, TAPESHO. And you can leave us a voice note. And then if we pick it, we'll feature it on the show and other people can know that you asked us a silly, ridiculous question.
So thank you so much for that. And finally, also a special thanks to those listening on Nebula. Nebula listeners get access to ad-free versions of episodes, and then also you can support us just by listening there. And you can join, you can get lifetime memberships, monthly memberships, you get to pick. But either way, go to nebula.tv/that'sabsurdshow to sign up, and we get credit for that. And it tells them that we sent you. So make sure you do that if you decide to join and support independent creators and podcasts just like us.
Yeah.
And as we say at the end of every episode,
be like a dolphin and live your dreams.
I don't even know what that means.
Dolphins can't dream, so they have to live it.
Be like a cockatiel.
Sleep with one eye open, lest Gritty comes.
No Gritty. As we always say, when your lungs crash against your ribs.
That's amore.